All right, everybody. So, welcome to the week whatever review video, week 6 review video. I was getting a little nervous because many of you were saying no questions, no questions, no questions, which is always great to see. It sounded like, for the most part, this lecture was fairly straightforward, but certainly we got enough little tidbits here and there, some loose ends, that it gives us plenty to talk about here. So this should be a relatively brief review video where we cover a pretty wide range of little loose ends, like I said, and try to give some clarity there. A couple things, though, that I want to point out before we do get started with the material. First off, congratulations, because if you're watching this, that means you've already, of course, watched lectures 9 and 10. And given that there are only 20 lectures in the entire course, that means you have watched half of the lecture videos for the entire course. And when this week ends, to be a little bit more precise, the middle of next week is the midterm week of the course of the semester as well. So a pretty big inflection point for us. We've reached, like I said before, the transition state of the semester, and beginning next week we are on our way down towards summer. Last thing that I will point out is that another inflection point is actually in the content. Part of the reason why these lectures might have seemed a little bit more straightforward than the lectures that you've watched previously is because we are stage setting. Most of the first half of this course is all about proteins and enzymes. Proteins first, and then enzymes as the subclass of proteins. And we do a lot of, obviously, protein structure, protein folding, protein modifications, post-translationally, enzymes, and enzyme kinetics. And it gets to be heavy duty, as you've all encountered already. The second half of the course, for all intents and purposes, is all about glucose metabolism. So we talk about glycolysis, the electron transport chain, the Krebs cycle, or the citric acid cycle, oxidative phosphorylation, and even when we talk about photosynthesis in plants, we're really talking about glucose synthesis. So it's fair to say that the vast majority of the second half of the course focuses in one way or another on glucose and how we strip glucose of its energy. Well, we strip glucose of its energy by stripping glucose of its electrons, and glucose is, of course, a sugar. So the point of this week really is to set the stage for glucose metabolism. We talk about redox reactions and standard states in Lecture 9 so that we understand the main reaction type we'll be using to get energy out of glucose. And then we talk about sugars in Lecture 10 so that you understand the basic chemistry, biochemistry of sugars in general, because, of course, glucose is a sugar. So let's dive right into it then. First loose end is this prime. What in the world do we mean by this prime? It seems to have not been as clear as I hoped that it would be. So this prime just basically says that when we are talking about standard conditions, we mean biological standard conditions. So standard conditions in chemistry mean a consensus agreement on how the experiment was performed. Some examples of this is 1 molar. We have a set temperature. We have 1 atmosphere of pressure. These are just general accepted guidelines across the entire field of chemistry that if you do an experiment in chemistry and you are at the standard state, you do that experiment under standard conditions, then you have that agreement. That's how you did the experiment. The pH, though, of the chemical standard state is far too acidic because it actually is 1 molar of free proton concentration, which is completely unreasonable for life systems, for living systems. So when biochemistry became a subfield, we moved a little bit away from the standard state, and we modified it just in terms of pH. We said for biological systems we need a neutral pH, so we need a pH of 7. And we indicated that biological standard condition with a prime. Previously, the standard condition had been represented with a superscript 0. So the example that we use in the lecture, which I think is a good example because it's something we're familiar with, is delta G, change in energy of a reaction. If you determine delta G using the standard chemical conditions, 1 mole of each reactant, 1 atmosphere of pressure, etc., then you've determined delta G under the standard state. So that's delta G 0. However, if you're determining the delta G of a biochemical reaction, you want to do that at a pH of 7 because that biochemical reaction has evolved to be optimal at neutral pH. That's the pH that we have. If you did that experiment and you determined delta G in a biological case, you would want to do that under the biological standard state. So you'd still have 1 atmosphere of pressure. You'd still use 1 mole of most of your reactants, but you'd have that pH of 0, a pH of 7, and we would read that as delta G 0 prime. So that prime just indicates that we're in the biological standard state, and to say it even more simply, the prime simply indicates that the pH of that standard state was a neutral pH that's friendly to biological phenomena. So that's really all that prime was meant to indicate. Redox reactions. It seemed like many of you were comfortable about redox reactions. A number of you did say that you remember redox reactions from general chemistry, which is great to see. O'Connors will be glad to hear that when I pass it along. But a number of you did ask for just a quick refresher, like a quick crash course to make sure that if we strip all the details away, you're comfortable with redox reactions, and I'm happy to do that, of course. So we're going to use a biologically relevant example here, not the generic example that we use in the lecture. So here we have an electron carrier, FAD. We're going to see FAD in a couple weeks again. It plays a big role in glucose metabolism. And FAD is carrying these protons, and wherever protons go in biological systems, electrons follow. So here FAD is in its reduced form. It's carrying electrons and protons. And we're going to mix FAD with another electron carrier called CoQ. We're going to see CoQ rear its head in the electron transport chain. And CoQ here is lacking protons, so it's lacking electrons. It's in its oxidized form. And this is going to be a fairly straightforward redox reaction. FADH2 is going to reduce CoQ. CoQ is going to oxidize FAD. In other words, the electrons and protons are simply going to change hands. So this is going to go to FAD+. Those protons are gone. This is the oxidized form of FAD. And CoQ is going to have accepted those protons and electrons. It becomes reduced. So a nice simple redox reaction. From left to right, we have FAD being oxidized and CoQ being reduced. Redox. Really what we want to focus on, though, and what we want to think about with these kinds of reactions are the half reactions of redox reactions. So we want those half reactions to be balanced. I'm sure that O'Connors or some other chemistry professor told you that for balanced equations or chemical reactions, everything you see on the left side of the arrow needs to imitate or mimic or account for everything on the right side. And these were called stoichiometrically balanced chemical equations. And that's true even for our half reactions. Right now we can see that everything is balanced. FAD is here, FAD is here, CoQ is here, CoQ is here, and 2 protons and the electrons that go with them are here and they're here. So this is already stoichiometric, it's already balanced, we don't have anything to worry about. We just want to take that same thinking with us when we go to the half reactions. So I'm going to start with what I already have here and say FADH2 goes to FAD+. That's one half reaction. And whatever's on one side of the arrow, I need on the other. So what I'm missing are the protons on the right side. So I'm going to add the 2 protons, like that, traveling freely. And wherever the protons go, the electrons go as well. So that's our half reaction for FAD. We've got FAD here, 2 protons here, 2 protons here, and the electrons follow the protons. So that's our half reaction for FAD. And then we have CoQ. So I'm going to start off by just copying what I already have. CoQ becomes CoQH2. And I want to balance that. Well, CoQ is present on both sides. I have my protons and the electrons here. So that means I need to add them over here to make sure it's balanced. I've got 2 protons, and the electrons that go with them. So now this is balanced. So these are my 2 half reactions. The last question becomes, well, what's what? In other words, which one's the half reaction of oxidation and which one's the half reaction of reduction? Well, oxidation is a loss of electrons. So here, FAD has the protons and has the electrons. It is one single thing. Let's use this as an example. This is FAD, and this is the protons and electrons. This is one thing, and it's represented by one term. What's happening over here is that FAD has become one entity, and the protons and the electrons have become the other. In other words, even though we're representing them all here on the right of the arrow, they have separated. FAD has lost the protons and electrons. The protons and electrons are now separate, and they're being represented as separate in the equation. So when something has electrons and then loses it, when something has electrons and then loses them, that is an oxidation. So this is our half reaction of oxidation. Now, if we use that same example here, here's CoQ, and here are the protons and electrons. They are separate. They're represented separately on this side of the arrow. And then when the reaction proceeds, the electrons and protons, they become one with CoQ. It becomes one term, it becomes one entity. In other words, CoQ took on or absorbed those electrons and protons. Anytime a molecule gains electrons, it became reduced. So this is the half reaction of reduction. So nothing new there, pretty much the same thing that we say in the lecture, but like I said, many of you asked to just have that refresher, and here we've stripped away all of the terminology, all of the foundation that I needed to give you, right? I had to go into the details in the lecture video to build the concept, but now that the concept's been built, we can hash out really what's relevant to us, and this is what's most relevant for us here. On to our next loose end, coupled reactions. What really is a coupled reaction? Here I am going to stick to the generic terms. We're going to have specific examples of coupled reactions later on in this unit, but I don't want to get too much into those weeds because it does complicate it. Once we start to talk about real chemistry, we've got a lot of things going on. So I'm going to stay generic here. So let's imagine one reaction, A, and let's say it's a cleavage reaction. So A is going to be cleaved to B and C. And let's imagine another reaction, and this is going to be a synthesis reaction. So let's say that C and D come together and are joined to synthesize E. So what we notice right away is that C is in common for these two reactions. C is a product of reaction 1, and C is a reactant of product 2. That allows these two reactions to be coupled. In other words, they can occur consecutively. A goes to B and C, C and D becomes E. Now that becomes important thermodynamically when this reaction is non-spontaneous. So if this reaction has a delta G that is positive, in other words, it's endothermic, it requires energy, and let's say it's a positive 70 kilojoules per mole, just to give it a value. And this reaction has an exothermic delta G, it's negative, and let's say it's negative by negative 110 kilojoules per mole. Now this has significant implications for the thermodynamic favorability of these reactions. Drawn as they're drawn here, the top reaction should not occur. It's non-spontaneous, it requires energy. Regardless of the transition state, we would expect it to have an energy profile like that. There's more energy in the products than in the reactants. The universe doesn't like to put energy into anything. So this reaction shouldn't occur. However, the universe loves this reaction, doesn't it? Because look at all that heat that's going to be given off. Look at all that entropy that is stood to be gained if this reaction occurs. The universe wants this reaction to occur, so this reaction is promoted. What does the universe need for this reaction to proceed? Well, it needs D, and it needs C. And where is the universe going to get C to make this very favorable reaction to occur? It's going to get C from the top reaction. So the universe actually sees, now I'm being a little bit anthropomorphic, right? The universe doesn't see anything, but the thermodynamic inclination is that this actually becomes one single reaction. It becomes a reaction of A goes to B and C, and then C and D become E. B is left as a byproduct. This is the coupled reaction from the universe's perspective, and this coupled reaction has its own combined coupled delta G. The coupled delta G of this reaction is negative 40 kilojoules per mole. In other words, the universe has lost its 70 kilojoules. This amount of energy went in to make this occur. So to make this happen, 70 kilojoules went in, and then allowing this to happen, 110 came out. That's a net gain of 40 kilojoules per mole. 40 kilojoules per mole is released into the universe when all of this happens as one. That's a favorable delta G, that's exothermic, that increases entropy, that's going to occur. So we can drive endothermic reactions forward in biochemical systems if they're coupled to sufficiently more exothermic negative delta G reactions. That's that coupled reaction. I'll say that again. We can have endothermic reactions occur biochemically when they have positive delta Gs, as long as a reaction that they are coupled to has a sufficiently larger negative delta G so that the net gain is energy release from the entire coupled reaction. And all you need for a reaction to be coupled is this. We need the product of the first reaction to be a reactant of the second. We're going to see this theme emerge again and again in Unit 2 and in Unit 3. We're going to drive unfavorable reactions forward when they're coupled. So keep that in the back of your mind. First in glycolysis, but even in the electron transport chain, we're going to drive a lot of things that the universe doesn't want to happen because we're coupling it to something just too enticing to let go. So that's the overall idea of coupled reactions. Now finally, for the first lecture, our last loose end is activating molecules. We used CoA as our activator in the example that we talked about in the lecture. Much like the reason why I didn't want to get into details just a moment ago for coupled reactions, maybe it was the wrong time and place to go into details for CoA. We'll talk about CoA specifically later on when we link the glycolysis to the citric acid cycle. So let's talk about activating more generally. So we have molecules that are non-reactive. And here's a great example for a non-reactive molecule. A non-reactive molecule has no free radicals, in other words, no unpaired electrons, and it has no charge, partial or full. This molecule is super content what it is. Electrons are balanced, there's no charge, there's no attraction for any other molecules. This molecule is completely inert. It is non-reactive. Getting this molecule to participate in chemistry, good luck, because this molecule is chemically content. Again, no attraction, no affinity for anything. It is balanced. It is content. But if we want to get energy out of this molecule, if we want to break these bonds, in other words, if we want to get this molecule engaged in chemistry, we've got a hard road to haul because it is so content and so inert. It's so non-reactive. We have to activate this molecule. We have to make it reactive. One thing that we often do biochemically, and by we I mean the biochemistry of cells, not we as scientists, but we as collections of cells, is we will add an activating group to this molecule. Maybe something like this. So if we add a carboxy group to this molecule, and we have that carboxy group act as an acid, it donates its proton, now we've added some reactivity here. This is now an activated molecule. It wants to engage in chemistry. We have a partial negative charge here, a weak one, but a partial negative charge here because of the electronegativity of oxygen, and we have a full negative charge here. This molecule is no longer content. It is hungry. It wants to interact with things. It wants to attack things. This is an attacking nucleophile. This is just like what we saw in the chymotrypsin mechanism. This is ready to make a new bond with something else. It's negative because of that unpaired electron. And this too is willing to have an affinity for something that's partially positive. So this molecule here is not content. It is not inert. It is not non-reactive. It's very reactive, and this will willingly participate in chemistry. So we, air quotes, we activate inert, content molecules by appending onto them very reactive groups. And we can convince and coax that inert molecule to engage in chemistry through that activation. So CoA was just an example of this kind of group. CoA is not a carboxy group, but it's this kind of thinking where we take something that has charge, that has reactivity, and we add it to something else. The molecule that we're going to see in just a moment is acetyl-CoA in a couple weeks from now. Acetyl is a very, very simple hydrocarbon. Acetyl is inert. Acetyl is content. It doesn't want to do anything. But we need to get energy out of acetyl. And we need to get this acetyl group to participate in chemistry, so we activate it by adding CoA to it. CoA is reactive, it's hungry, it's antsy, and now acetyl-CoA, will engage in chemistry where acetyl itself wouldn't have before. And this is acetyl. I forgot the L. So really that's all we were getting at with activation. Again, just laying groundwork. Okie dokie. So that's the lecture 9 loose ends, and we're only at 20 minutes, so that's great. So now let's tie up some loose ends from lecture 10, and we're going to move into the prop portion of this review video, because sometimes it's easier just to show these things rather than explain them. But the first thing that I was asked for was to go over some terms. It seemed like just the terminology in general was confusing to some of you, so let's talk about the terms and what they mean. Well, the first term that we want to talk about is the prefix in front of os. Os tells us that we're dealing with a sugar, just like ace tells us that we're dealing with an enzyme. And classes or categories of sugars fall into oses, where the prefix indicates the number of carbons. So we have trioses, 3 carbons. We have pentoses, 5 carbons. We have hexoses, 6 carbons. Glucose is a hexose. Ribose is a pentose. Ribose has 5 carbons. So os always means sugar, and the class of the sugar, its prefix always gives us the number of carbons there. So that's the first thing that we want to talk about. Another way of classifying sugars gets at their chemistry. So we have aldoses, there's that os, so we're dealing with sugars, and ketoses. Aldoses and ketoses. Here I just went a little too quick probably and said, aldoses and ketoses, it just has to do something with the double bond, but don't worry about it. And much to many of your credit, you did worry about it, and good for you for asking. So let's go into just slightly more detail there. For aldoses, the double bonded carbon, the carbon that has a double bonded oxygen on it, is carbon number 1. It's the first carbon of the ring or the first carbon of the chain. Remember, we number our carbons, and so carbon number 1 has the double bond. In ketoses, it's the second carbon that has that double bonded oxygen. Carbon number 2 is double bonded. Carbon number 1 is this group here. So that's the difference between the two. Aldoses have a double bonded oxygen on carbon number 1. Ketoses have a double bonded oxygen on carbon number 2. And that's all we really need to know about that. Then we go to Pyrinoses and Furanoses, or Pyrinos rings and Furanos rings. So we have Pyrinos, sugar, Furanos, sugar. And these terms don't get at how many carbons there are. You can have a 6-carbon Pyrinos, you can have a 6-carbon Furanos. It gets at the shape of the ring or how many carbons are in the ring. So Pyrinos rings have this hexagonal shape where every single carbon is a member of the ring. And Furanoses are pentagonal, not hexagonal, where if we are dealing with a 6-carbon sugar, that 6th carbon is outside of the ring. So Pyrinoses, 6-membered ring, Furanoses, 5-membered rings. Again, they're not talking about the number of carbons. There's 6 carbons here and there's 6 carbons here. It's the shape those carbons take when they are in their ring. So this is where I thought we might need our first prop. So here I've got, embarrassingly enough, 3 torn-in-half gummy bears that are then coated in flour, because when I was doing this to make sure it would work, it was sticky, and it was pretty skeevy that this would keep sticking to my fingers, and so I covered them in flour just so they wouldn't be sticky. So what we see here are 1, 2, 3, 4, 5, 6 of these carbons in a row, 6 carbons held together in a chain. So this is a hexose, a 6-carbon sugar, and it's always going to be a hexose. There's always going to be 6 gummies here, and it's always going to be a hexose sugar. But it can be Pyrinos or Furanos depending on the ring that it forms. So let's make the Pyrinos ring first. So that's going to be a hexagonal ring. So I'm going to do this, and then if I can just coax that so it looks like a bond, close enough. So you can see there, that's that hexagonal shape, right? Whoops. So we've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. All 6 carbons are in the sugar, and we've got a 1, 2, 3, 4, 5, 6-membered ring. That's our Pyrinos hexose sugar. Now, no magic, right? I'm keeping this one string here. It's still 6 carbons. Let's make this a furanose now. So to make this a furanose, one of these carbons is going to lie outside the ring. And then we're going to have a pentagonal shape rather than a hexagonal shape. So let's see if I can make this a pentagon. Again, I want to get that bond there if I can. Let me just see if I can coax that string to make it a little bit more accurate. Come on, string. That's probably the best I'll be able to do there because the string is not fully cooperating. But there's the pentagon. So this is carbon 1, we'll say here. And then we're going down to the pentagon, first membered ring, second membered ring, third membered ring, fourth membered ring, fifth membered ring there. So that's the ring, but then we have that last carbon coming off here. So it's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. That is our Furanose ring. So Pyrinos and Furanose are terms that get at, however you want to think about it, the shape of the ring, right? Pentagon versus hexagon, that's perfectly reasonable to think of it that way. The number of carbons within the ring, that's equally valid. 6 carbons in the ring, 5 carbons in the ring. But that's the difference of what those terms are meant to indicate. Now, number one kind of inaccuracy is that some students think that Pyrinos and Furanose are synonymous with chair and boat. Not true. There is no chair and boat with Furanos rings, only with Pyrinos rings. So if we go back to that hexagonal ring, if we were to take this corner and bend it up and take this corner and bend it up, we would make the boat configuration. And if we were to take this corner and bend it up and take this corner and bend it down, we would make the chair configuration. What am I talking about? Well, second prop. So here's the hexagon, right? This is the Pyrinos sugar. 1, 2, 3, 4, 5, 6 vertices, where each vertex is a carbon. We can take this end and bend it up in 3-dimensional space. And take this end and bend it up in 3-dimensional space. And then we get the boat form. Can you see that kind of boat shape there? That's the boat configuration. That's what I was drawing there. So if we see it on its front, we see that it's the Pyrinos ring. If we look at it on the side, we see that it's the boat conformation. But if we keep this bent up and we bend this one down, that's the chair. It's like a lounge chair, right? Where you'd rest your head here, your butt would be right here, and you're resting your legs, you're dangling your legs here. So if we look at this on its edge, we can see that chair configuration, up, down, and that's what we're trying to draw here, up, down. So boat and chair are both conformations of the Pyrinos, not of the Furanos. And in terms of favorability, thermodynamic favorability, we've got hydroxyl groups coming off each of these. So when we go into boat form, these hydroxyl groups, they tend to collide up here. They tend to get in each other's way because they're both up here in basically in a cis conformation. They're on the same side of the molecule. Once we go into chair, well, now we've got a bulky hydroxyl up here. We've got the other bulky hydroxyl down here. There's much, much more room. So that was the other point we were trying to make in that lecture. If we do boat, we have steric interference here. If we do chair, we don't. So chair tends to be the more preferred form. So which is the preferred form of Furanos rings, boat or chair? Don't think of it that way, because in order to make a boat or a chair, you need a hexagon, and Furanos rings are pentagonal rings. So what happens in a pentagonal ring? What happens for Furanos? There we just get the endo conformation. Endo is a pucker, and a pucker is where one of these carbons, one of these vertices, comes up. And that's it. That's kind of like the envelope flap I talked about in the lecture, almost like you're folding down an envelope. We just get that pucker. So this is what Furanos rings do, pentagonal rings. Now we can have endo 1, which means carbon 1 has puckered. But we can have endo 2 as well. What would endo 2 look like? Well, we would just make that planar. We'd go to carbon number 2, and carbon number 2 would be our envelope flap. That's endo 2. And you can have endo 3. What would endo 3 look like? That's when the third carbon is the puckered carbon. And you can have endo 4. You can do an endo. You can do a pucker with any of the carbons in the Furanos ring. It's just only with one of them. So no boat, no chair, only an endo form for Furanos rings, and the endo form is that pucker, that out of the plane of the Furanos ring. This is coming up, everything else is planar. That's what we do for Furanos rings. So that covers a lot of ground in 10 minutes. Hopefully that helps not only with terminology. All of you know by now. If you haven't had me before, you've certainly learned it this semester. And if you have had me before, you've heard me say it many times before. Don't care about terminology, right? We're not in here to memorize biochemistry because memorizing biochemistry is not possible. We're here to understand. So I'm trying to link terms like os, aldose, ketose, furanos, pyranose. I'm trying to link those, but I want them linked with the concepts. It's the concepts that really matter, so that's what we're spending our time on even here. Last thing I wanted to touch on, just super quick, because it is a term that we're going to be seeing again and again, this glycoside or glycosidic bond. So a glycosidic bond is a bond between two sugars. That's really all a glycosidic bond is. So here I have two, what kind of rings? Ah, perfect. I heard someone say it, Pyrinos rings. These could be glucose rings because glucose is a 6-carbon sugar, but it doesn't have to be. So we have two 6-membered rings, two Pyrinos rings, and they're held together now. So this is a disaccharide, a double sugar. The bond that's holding these two sugars together, a sugar-to-sugar linkage bond, is a glycosidic bond. That's all a glycosidic bond is. Now, we could have glycosidic bonds that are in cis. We can have glycosidic bonds that are in trans. We can have glycosidic bonds between different carbons in each of the sugars. We can have glycosidic bonds between different sugars, like fructose to glucose or glucose to galactose. Glycosidic bonds are extremely varied. There's really only one way to link one nucleotide to another. It's a phosphodiester bond, and it's from the 5' phosphate to the 3' hydroxyl. There's only one way to link two amino acids together. That's a peptide bond, and that's a bond between the first amino acid's carboxy group and the next amino acid's amino group. There are dozens, hundreds of different glycosidic bonds. There's a million different ways. Well, not really a million. There are a lot of different ways that you could link two sugars together. So the variety of glycosidic bonds is huge. But whenever we say a glycosidic bond, we do mean we're holding one sugar to another. And that's really what we want you to get out of that. Different enzymes are needed to make each of the different unique glycosidic bonds. Different enzymes are needed to break each of the different glycosidic bonds. We'll touch on that just a little bit in our challenge questions this week. But we do want to know the kind of the bare bones foundation that a glycosidic bond is a sugar-to-sugar bond. Okay. I think that's really all we needed to cover. See, I told you we would cover a lot, but we would do it in a short amount of time. Just a lot of loose ends. No major concepts here, just things that we want to tie up and tidy up so that our understanding is solid as we move forward. You're going to be seeing redox reactions again. You're going to be seeing sugars again. You're going to be seeing glycosidic bonds again. Everything we talk about this week, you'll be seeing repeat itself over and over again as we go into glucose metabolism. So important that we're comfortable with these foundational concepts, and so important that we're comfortable applying them to material that we encounter in the upcoming weeks. So, congratulations on finishing lectures 9 and 10. Congratulations on finishing the 5th review video of the semester. Certainly another midterm inflection point. You will be finishing your 5th set of challenge questions in a couple days, and the end of this week will mark the midpoint of the semester. So congratulations to all of you for doing such a phenomenal job, for working through the pandemic, for sticking with this asynchronous class, and for learning. If you have anything that's still bothering you, please let me know in the dialog box that's going to pop up right now.